Good morning. Today is February 11, Tuesday, 11 a.m. So this is Advanced Topics in Data Storage, Lecture 6. Today we're going to discuss ISBN and Galois fields. So ISBN, do you guys know anything about ISBN? We have a number on the back of every book named ISBN number, right? So that's the same thing, ISBN. Okay. So this is the course outline. So we are at Galois field. So we are into complex Reed-Solomon coding and diagonal parity. So we are at block-based protection. We have finished our basic RAID RDP, RAID DP, Hamming code, basic bit protection, and we are at the second point, which says block-based protection. Okay. So RAID DP versus RAID 6 PQ. So before starting this lecture, if someone wants to see the RAID RDP, which we discussed on board online. So yesterday, Professor Wilner did that again, and he recorded it perfectly instead of like swapping the screen while recording. So if someone wants to go there and look at the recording, they can just watch the yesterday's recording for RAID RDP. And yes, RAID diagonal parity is an engineer's solution. Find a way to add additional parity using the same XOR algorithm as already used in RAID 4. So we have discussed RAID 4, the same XOR algorithm, but it's the engineer's solution. So something which they come up to a way to add additional parity. Okay? So we're adding an additional parity, but something different than we discussed previously. So RAID 6 parity, PQ parity is a mathematician solution. Find a different kind of parity calculations using finite field algebra. That's Galois field algebra. So Reed-Solomon coding is one of the example we can say for finite field algebra. So in order to understand Galois field algebra, we start back in 1966 with the invention of standard book numbering. So then they need to assign a number for every book they publish. So then they come up with this idea to number every book using standard book numbering. So that was in 1966. So ISBN, it's in International Standard Book Numbering. So we have two formats. We only have one format now, but we used to have one more format back those days. So a classic 10-digit number, and the present ISBN number we are using is 13-digit number. So 10-digit number, Galois field of size 11, so 1 each check bit. Based on original 9-digit SBN, 1966, British Publishers Association. And 13-digit number, more numbers, weaker checksum, that was introduced in 2007. So in this class, we're going to discuss about 10-digit number. That's Galois field because this was on Galois field. So we're going to discuss 10-digit ISBN number. So there is an overlap period between 1980s and 2007. So on some of the books published on those years, we can find both 10-digit ISBN and 13-digit ISBN. So both formats are n digits plus one checksum. So for 10 digits, we have 9 digits and one checksum. And for 13 digit, we have 12 digits and one checksum, the check digit. Yeah. So we will focus on 10-digit versions. So you can see the ISBN numbers. On the top book, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a 10-digit ISBN. So here 7 is the checksum. And these are the numbers. Here 039475817X, X is the checksum. And these are the 10-digit ISBN number. And here we can see, I guess, this one. This one is 13-digit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, this is 13-digit ISBN number, 12 digits, and 9 is the checksum here. So ISBN number only have digits, not letters. So these three are 10 and this one is 13. So imaginary conversation in Britain in 1966. So this should be in British accent, but I'm not good at British accent. So you can imagine speaking me in British accent. Yeah, so why we need a better way to track our book inventory. So this was the imaginary conversation back in those days. Yeah. Why don't we just assign every number a book? Every book a number. Yeah. So obviously, but what if someone mistypes the number? So back those days, there were no barcode readers. So everything need to be entered manually in 1966. So what if someone enters a digit wrong? Yeah. What if someone mistypes the number? Oh, let's see. Let's add a check digit at the end. So we'll add a check digit at the very end of the entire number to see if the number was typed correctly. Okay, how does that work? Like this. So calculating ISBN check digits the old way. So the first digit is language. So they have a number for every language, 0, 1, 2, 3 for English, Spanish, everything. Okay. And this is the publisher code. 394 is the publisher code. And these three digits were given to publisher code. Book identifier has 1, 2, 3, 4, 5 digits and one checksum. So this checks whether this number was correctly printed or not. Okay, so this is how ISBN is in the old format, the 10-digit ISBN format. Simple. So we multiply every digit with the respective 1, 2, 3, 4. So we'll just multiply these things. We'll multiply the first digit with 1, second digit with 2, third digit with 3, and so on till the checksum, check digit. So we are discussing how to get a check digit now. So, okay. So we just multiply 0 times 1 is 1, sorry. 0 times 1 is 0, 3 times 2 is 6, 9 times 3 is 27, 4 times 4 is 16, and so on. And we'll just add all the numbers we get. Okay. So we don't know check. So we're just eliminating that for now. So we'll just multiply each digit and then add all the digits. Okay. 0 plus 6 plus 27 and so on. And we'll mod it by 11. Okay. So if we add these, we'll get 302 and then mod 11 gonna be 5. So we'll put 5 in the check digits. So the whole thing adds to a multiple of 11. So now 5 times 10, 50. So 302 plus 50, 352 mod 11 is 0. So our target is to do, to get a number that exactly divides with 11. So we're adding a check digit to do that. Okay? So this is how we calculate ISBN check digit in the old way, like 10-digit format. And then check digit is 5. So what good does that do? So why are we doing that? Well, suppose someone transposes 2 digits, for example. If any one of those 2 digits, instead of 947, if someone mistypes 974, what happens? So dealing with transpositions. So here, this is the number we have just discussed. This is the right way to type ISBN ISBN 10-digit code onto a book. But what if someone mistypes 2 digits? So instead of 75, here there is 57. So this is wrong. Even the spelling was wrong. So 0 times 1, 3 times 2, 9 times 3, and so on. We get 354. So 354 mod 11, 2. So we know something was wrong in the digit, in the ISBN number, because it's not adding up and giving it an exact multiple or exact division of 11. So we know something is wrong. That something is mistyped in the digits. So imaginary conversation. So you see, if someone gets a digit out of place, the checksum doesn't add up to multiple of 11. So that's the thing we already know. Yeah, it's easy to know. Well, that's very nice. Can it correct the error? Not exactly. It can correct a missing digit though. Yeah, if someone mistypes a digit, we can correct it. But if something is like, we can do the missing digit, but we can't correct a mistyped one or exchange or, you know, mistyped one. Note, it's an eraser code. So correcting a missing digit. So let's take the ISBN code again and let's miss a number here, right there. So 0394 asterisk something, the symbol 55995. So this one is missing. So let's add it. 0 times 0 is 0, or 0 times 1 is 0, 3 times 1, 3 times 2 is 6, 9 times 3 is 27, and so on. We don't have this. Let's just keep it 0. So it comes 317. If we add up these digits, we get 317. Now 317 mod 11 is 9. So what we'll do now? So the missing times, the fifth digit is missing. 1, 2, 3, 4, 5. So this missing times 5 plus 9 should give us 0. This is from basic algebra. So now minus 9 by 5, it's going to be 2 times 9 is 7. So this is something we are not aware. It's not the basic arithmetic step, because minus 9 by 5, it's going to be some other than 2 times 9. So minus 9 times 1 by 5, 2 times 9, 7. No, that is that is not what we learned so far. So of course you need this multiplication table. So this is the multiplication table we need to look at while doing that. So if we go back, it's 2 times 9 is 7. Let's see. 2 times 9 is 7, or 2 times 9 is 7. So this is the value we put it out there. And what's 1 by 5? So 1 by 5, 5 and 1, it's going to be 9. Yeah, or 5 and 1, it's going to be 9. So 1 by 5 is 9. So we are using this multiplication table to solve this. Yeah, but here we see 2 times 9 is 7 and 1 by 5 is 9. But multiplicative inverse in modulus, so that's a wrong table. 2 times 9 is 18, not 7. But you see this times table is modulus 11. So we are doing mod 11 if the number exceeds 11, okay? Or the number exceeds 10. So 18 mod 11 is 7. So see now, if you go back to this table, 1 times 1, 1, 1 times 2, 2, 1 times 3, 3, and so on. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 8, 2 times 5, 10, 2 times 6, 12. So it's exceeding 11. So we are doing mod 11. 12 mod 11 is going to be 1. So we're putting it 1 here. And the same way, 7 times 2, 14. 14 mod 11, 3. So this is how we generated this table. So this is GF11, Galois field 11 table. Okay. So any number that exceeds 11 gets chopped down and fits until it fits. 18 times mod 11 is, 18 mod 11 is 7. So that's how we created the table. So what about 1 times 5 turning into 9? Well, you see where 5 times 9 is 1. So that means they are multiplicative inverses. Yeah. Multiplicative inverse, is that a joke? So this is the conversation, sir. Okay. Multiplicative inverse, y is the multiplicative inverse of x if x times y is 1, right? So in the table, if we get multiplied by two numbers and a 1, so those two numbers are multiplicative inverses. So in real numbers, 4 by 3 and 3 by 4 are 1, 4 by 3 times 3 by 4. So those two are multiplicative inverses. We know that. So 5 times 0.2 is 1. So 5 and 0.2 are multiplicative inverses. 1 times 1 is 1. So number itself multiplied by, I mean, a number multiplied by itself is the multiplicative inverse as well. So I assure you, sir, I'm not joking. In modular arithmetic or a prime number, there are no fractions. The inverse is an integer. Okay? So if you see here, how that works. So 2 times 6 is 12. 3 times 4 is 12. Okay, so 12 mod 11 is 1. So as we saw in our table. So again, 5 times 9 is 45, 7 times 8 is 56, 10 times 10 is 100, so on. So here you see 4 times 3, 4 and 3 are multiplicative inverses, and 3 and 4 is multiplicative inverse. So you can see here. So 2 and 6, 6 and 2. So these numbers are multiplicative inverses of each other. So as we saw in our table, so on. So if we go back to our table here, so 3 times 4 is 12 mod 11 is 1. So 4 and 3 are multiplicative inverse. And again, 3 and 4 are multiplicative inverse. So that is how we get a multiplicative inverse from the table. So we now saw how to create a Galois field 11 table and how to solve those arithmetic questions we have. So any questions from these slides till now? So this was easy. Exercise for students. So anyone interested to try this question? And again, what does this X mean? It's 10, yes, Roman number. Yeah, it's a Roman number. It's not X, it's 10. So 039475, something we do not know the number. I mean, the missed number 17 and X. But why can't we represent it in A? 10 is A in is the Roman number for 10, of course. Why can't we use A like proper hexadecimal? Because I'm a 1966 bookseller, not a 21st century computer scientist. So we don't have hexadecimal numbers back then. So those are represented with Roman numbers X. Okay. So that's 10, not X. So anyone's interested in doing this thing? I mean, solving the question. I can show you the table. Galois field element table. We have time. We have time. It's a short lecture. Yeah. So what's our first step? Yeah. So we just multiply these numbers with 1 times 1 times 2, 3, 4, 5, 6, this times 7, 8, 9, and 10. What do we get? 0 times 1, 0. 3 times 2, 6. 9 times 3, 27. 16, 35, 30, This is unknown number. Let's keep it 0 for now. 8. This one is, and this is 100. What if we add these things? Here we are. And if we add this thing, yeah, 285. What's the next step? Mod 11. What do we get for mod 11? Yeah, it's not 1, it's 10. Okay, so now the missing times. So missing digit 7 plus, what's the mod? 10. So we should get this to 0, right? This should be equal to 0. Okay, what's this one? 1 by 7 times minus 10. Minus 10 by 7. So let's go back to our table. It's 1 by 7. And let's see our table. So check the multiplicative inverse of 7. It's 8. So 1 by 7 is going to be 8. 1 times 10 is going to be 10. 1. So this is where we are. Oh, we have finished all these slides. 285 mod 11 is 10. So 7 times 10 is 0. Minus 10 by 7, 1 by 7. So if we find it, it's 1. The multiplicative inverse is 8. So 8. Therefore, the missing digit is 8. And again, after placing 8 here, if we do it, we'll get mod 11 as 0. So, see, it's 8. We just found it to be 8. So this was taken from this book. And these are the sources we have. So Bookfinder, if we go into this link, we can enter the ISBN number and we can find which book it is. Okay. Let's see. Let's enter the ISBN number. This one. 0394758817X. One of the road, hitchhiking through an Australian outback. So by entering the ISBN number, we can find the book name from these websites, which we have seen. And again, Richard Tuo ISBN page. If we go to this link, you can see the explanation of mod 11 and mod 10, the ISBN numbers, and the modern 13-digit ISBN numbers explanation as well. You can just go through this link if you are interested. And there is the video from the YouTube as well. Now, what does ISBN have to do with a RAID? Why are we learning ISBN concept for RAID? No, it's not. So, so let's see if this is disk 1, disk 2, disk 3, and so on till disk 7, and the check digit is parity. Okay, so instead of like depending on the entire block, disk block, we can just see the row and we can have a parity, and we can get to know if a digit is getting missed. Let's see, instead of reconstructing a digit, we can reconstruct a drive. Different sum check for XOR. If two drives fail, we can reconstruct by comparing XOR and ISBN-ish OR. Modulo 11 arithmetic is not convenient. Can we use power of 2? Yes. Timetable mod 8. So we have just seen mod 11. So we're doing mod 8 now because it's exactly we can represent it in 2 times, 2 power something. So let's see for 8. So here is 7 and 5 times 2 is 10. Mod 8 is 2. And again, 6 times 2 is 12. Mod 8 is 4. 7 times 2 is 14. And mod 8 is 6. So in the same way as we constructed our mod 11 table, we're constructing mod 8 table now. So that didn't work so well. 2, 4, and 6 have no inverses. So this is not a Galois field. So here you can see we need to have 1 in every row to get a multiplicative inverse. So here most of these values do not have multiplicative inverses. So 2, 4, 6, if you see 2, there is no multiplicative inverse. For 4, there is no multiplicative inverse. We have zeros instead of ones. And if we see 6, we have zeros instead of 1. So this is not a Galois field. We do not have 1. So we do not have multiplicative inverse for every number in this table. So we can't use this table. So Galois. So he's a French mathematician. He just lived 21 years, I guess, his lifespan. So he born in 1811 and died in 1832. So made major advances in group theory, sent them to a friend one night, and then fought a duel the next day and died the day after that. So most of the mathematicians have some fascinating stories. Yeah. So he just sent the work to his friend. Some of the mathematicians. Back in those days when we study like 6th or 7th standard, so for every chapter there used to be a mathematician story, and most of them are interesting. Something like like these stories. They fought in the duel and died. Yeah, so most of them have that, I guess. We need to know. Yeah. One night he sent his story to, I mean, his mathematics works to his friend, and the next day he fought a duel and he died in the duel. So most significant of contributions of finite Galois field. So integer mod p is a finite field because p is a prime number. Integers mod p power n, where n is an integer, is a finite field. If a proper primitive polynomial is chosen, what's primitive polynomial? We're going to see. And most famous contribution, a novel proof that is no quintic. So times table gf 2 power 3, that's 8. So this is a primitive polynomial x cube plus x plus 1. So we use this primitive polynomial to construct a Galois field table for 8. So if you see here, we have multiplicative inverse for every number. So if you take 1, 1, 1, 2, and 5 are multiplicative inverse, 3 and 6, 4 and 7, 5. So we have multiplicative inverse for every number. So this is something that's constructed, which was better than we discussed previous table. So that's better. Every number has an inverse. But how did we do that? How did we constructed this table now? So using logarithms. We have already discussed logarithms in our very first lecture, plus a primitive polynomial. 6 Let's remember 4 times 4 is 6 in this table. And let's see how we got 4 times 4, 6. Okay. So we know this formula, x times y. So antilog of log x plus log y is going to be x plus y, I mean x times y. We know this formula. So 17 times 35. So log 17, 1.23, and log 35, 1.5441 if you use a calculator. And if we add those two, we get 2.7445. So antilog of 2.7445 is 595. Okay. So how did we get that? We can use this scale, sliding scale, to find the logarithms. I guess it's better if we have this in class. No, we'll show it in tomorrow's class, next class. We'll synchronize both the classes. Yeah, so you can use this scale to see the logarithms and anti-logarithms, to find the logarithms and anti-logarithms. We have calculators to do that now. Back in those days, they used this sliding scale to calculate. So building a multiplication table in Galois field. So how did they build that table? 2 power 8 primitive, using a primitive polynomial. So choose a base prime. Computers prefer 2. So choose a number that is power of the base 4, 8, 16, 32, and so on. So choose a primitive polynomials. So we'll discuss the details later in the next lectures, I guess. So build a table of powers, also known as anti-logarithms of the base, and read the table backwards to get the table of logarithms. So use powers and logarithms to build the multiplication table. We're going to see an example and you will get to know how we did that. So choose a primitive polynomial. So example, x cube plus x plus 1 or x cube plus x square plus 1. Plug in a base prime number, for example 2. Just substitute 2 in x values and we'll get a number. So if we substitute x 2 in place of x, 2 cube plus 2 plus 1 is going to be 11, or we say b in hexadecimal, or in binary 1011, 1011. And here is another primitive polynomial. We just plugged in 2 in place of x and we got this one in hexadecimals and in binary as well. Next, calculate a power of powers of 2 mod 8 by shift left 1 bit. If the result is greater than or equal to 8, because we're doing it for 8, we'll just mod it. We'll just XOR with the polynomial to bring it back in range. Okay. So we'll see an example. Let's use x cube plus x plus 1. It's 11. So we're using this primitive polynomial to build Galois field of 8. So now, antilog on Galois field 8, x cube plus x plus 1. So plug in 2, we'll get 11, or a. So for 0, we have 1. For 1, we have we are just squaring, or we are just 2 power 1 is 2. Sorry, 1 power 2, or 2 power 1 is 2. Again 2 power 2, 4. Again 2 power 3, 8. Now it's 8. So we're XORing it with 11 because it's a Galois field 8. So if it exceeds 7, we'll just mod it with 11. Why 11? Just plug in 2 in place of x, we'll get 11. So we'll XOR it with 11. So 8, 1, 0, 0, 0, XOR 11, 1, 0, 1, 1. So 1, 0, 1, 1. So it's going to be 3. So for 3, it's 3. And we'll again XOR, we'll double this number. 3 times 3, I'm sorry, 3 plus 3 is 6. 3 times 2 is 6. And again, 6 times 2 is 12. We're XORing it with 11. We get 7. And 7 times 2 is 14. We'll XOR it with 11. We'll get 5. And 5 times 2 is 10. We'll XOR it with 11 and we get 1. So 1 already exists in this table. So it repeats. Again, we have 1, 2, 4, 8, 6 for 7, 8, 9, 10, 11, and so on. So this is how we build a Galois field table of 8 with primitive polynomials. So any questions in this table? It's simple. We'll just take a number. we'll do 2 power that number. If the number exceeds this primitive polynomial, we'll just mod it with, we'll just XOR it with that primitive polynomial number. We'll cut it off and we'll get that number, and then we multiply that number with 2. And if it again exceeds the number 8, or if it's equal to or greater than 8, we'll just XOR it with the primitive polynomial, and we'll do it until we see some repeated values. Example 1. So we have 1 here, we got repeated, we'll just stop it building over there, and we'll just repeat it. For 8, it's going to be 2, for 9, it's going to be 4, and so on. So this is how we build a Galois field table using primitive polynomial. Next. So derive logs from anti-logs. It's opposite, right? So 0, for 0, it's 1, for 1, it's 2. So for now 2, it's 1, 4, it's 2, and so on. Okay. So we're just changing these things. Yeah, now see. Log n. So now just change the label. So going forward, I will use the 3-column table with n in the middle, log n on the left, 2 power n on the right. Yeah. So like this, log n, 2 power n. Now 4 times 4, anti-log of log 4 plus log 4, right? So it's the formula we discussed. Log 4 is 2 from the table. Okay. 2 plus 2 is 4. 4 times 4, anti-log of 4 is 6, again from the table. So therefore 4 times 4 is 6, using this Galois field table. So next lecture, from 2 power 8 to RAID 6 cube parity. So this we'll discuss it in the next lectures. And this is the last slide. Some references you can go. Slide rule, Galois field calculator. We have some calculators. We can just give the primitive polynomial and give the base number, and they'll calculate the tables for us. Yeah, so if we go into this, the multiplication in GF8 based on x cube plus x plus 1. So this is how they are doing the multiplication. If you can do addition, subtraction, and so on using the numbers, using primitive polynomials, or oops. Oh. And this is the multiplication table. We can just build the multiplication tables in this link. Okay. So we're building 2 power 3 x cube plus x plus 1. So if we ask it to generate tables in hexadecimal, so this is the table we got in hexadecimal. Or you can use different colors to generate tables. Light color for less values and more bright colors for greater values. So you can see the table was built in these links. So you know how to build the table. So you can just build your table and can verify here. We have different primitive polynomials right there. And you can generate the tables for different primitive polynomials. So see, it increased. Let's do it for some higher number. You see larger tables. So you can use these links. You can play with these links to generate primitive polynomials or GF tables. Yes, RAID 6 or GF discussion. You can go through here in the blog, error recovery in RAID 6 and stuff like that. And that's the end of the lecture. Any questions in this lecture? It's easy. We just discussed how to about ISBN 10. You can also get to know about ISBN 13 if you are interested in the links. And we linked that ISBN to the RAID 6, which you're going to see in the later lectures as well. And we discussed Galois field, and we discussed building Galois field tables with primitive polynomials, using primitive polynomials. We'll see what are primitive polynomials in the next lecture. So we have started our discussion for Salmon coding. So you will see the next few lectures for Salmon coding. It's, I guess it's a little complicated concept, but yeah, let's see how that goes. And now we have a homework that was already in the blackboard. Let's see what that homework is. We go down to homework. We have a medium homework, 3 Hamming code. Uh, I guess this was done, but a few of the students have not yet entered in Excel sheet. So just go and put some numbers to get your points. It's an easy point to get. So just fill it out if you have missed entering the numbers, because it's easy. We can do it, but you won't get your points. So just go there and fill beside your WSU IDs with Hamming code. Next. No partial credits. They haven't done any work for homework. So yeah. And Hamming decode. So we have any homeworks posted?
Yeah, 5.
5?
Big homework.
Okay.
5.
RAID DP enhancements.
So that is the RAID diagonal parity.
So we have IPYNB file. You can download and play around with that. So download the IPYNB file, add your WSU IDs to the beginning of the downloaded file. So add a new initialization method to initialize data drives. So this is the function. So just use the name to get the function. Every data block to its stripe number to the non-existing diagonal stripe. Pick whatever reasonable value you like. Add an optional how argument to the dump drives function to change display formats from binary to hexadecimal and so on and so forth. The default method here is short underscore hex. Add at least one new method, short underscore decimal. Okay. And add a new cell at the bottom of the program to create 14 drive 22 block RAID DP. So we already have a RAID done in the program IPYNB file. You just need to do it for a bigger number. Fully initialize starting with a diagonal stripe pattern, dump the data in short decimal. Okay. So it's not easy or it's not complicated homework. You have code, you have file. We have done some work in that. You just need to extend the work. That's it. So add some functions and build a new RAID DP with a bigger number, and save the file with your WSU ID in the start and submit the work. That's an easy homework for now, if you know the concept of RAID. And again, we have LLM models to get the code for us. So if you know the logic and if you know how RAID works, it's an easy homework. Yeah, that's about the homework. Let me stop recording the lecture. Any questions?